grade 12s. Well, today we are going to carry on with our chemical equilibrium. Remember, we discussed that last week, and we looked at Le Chatelier and we looked at Casey. We're going to add a little bit more on that because we know that's a difficult section for you guys. So to start off with, I first want to make sure you know some terms because they're going to come up often. Okay, and these are new terms. They're not the same ones as we did last week. So here we go. Here are my terms, and that's the yield, Harbour process, and contact process. This should take you really, really quick. So I'm only going to give you 1 minute this time to discuss these, and your minute starts now. So, grade 12s, how did you do? And I'm pretty sure some of you are going, but what's this got to do with equilibrium? Well, actually, it's got a lot to do with equilibrium because remember, just doing our equilibrium in general terms or just any sort of equation doesn't really help us, okay? And the Harbour process and the contact process are both very important processes for South Africa. You're going to do them again in a lot more detail than I'm going to look at today when we do fertilizers near the end of the year before you write prelims. So actually they're very, very, very important. And you should have seen the Harbour process before now. So let's just remind ourselves a little bit of what we were doing. So remember, when we look at this, okay, so we're looking at the applications of Le Chatelier's, and the things we've got to look at when we look at the applications is we've got to consider the rate of the reaction. That's really important, okay, particularly when we consider that rate affects yield. And in industry, the yield is incredibly important. The more product we get, the more money we can make, okay? But we have to get that product at a suitable rate, so it's got to go fast enough. Otherwise, if it's too slow, then we don't make money. Because remember, in industry, time is money, okay? Added to that, that yield is actually also affected by the equilibrium constant. So knowing what the equilibrium constant is for a particular reaction helps us decide whether the yield's enough. And in fact, when new processes are being developed, they have to look at what that equilibrium constant will be at certain temperatures, and then they can make a decision as to whether the yield is worth making, okay? Whether you get a high enough yield, in other words, a high enough percentage of product per unit time that it makes sense to do it, okay? And that's what we consider when we look at the contact process. Contact process, okay, remember, creates sulfuric acid, and the Harbour process creates ammonia, okay? And when we do fertilizer later, I've got interesting stories about the Harbour process, so it's actually quite important, and why the contact process is called the contact process. We're not going to worry about that now. But using Le Chatelier's principle, which is what we did last week, okay, that Le Chatelier's principle, we looked at temperature, pressure, catalyst, all of these things, and we've got to consider how these things, temperature, pressure, catalyst, etc., affect the yield in my industrial processes, okay? So we need to have those. Now, what that means for you grade 12s is when we get there is that there's certain conditions around the Harbour and the contact process that you have to know. So these are the things where you get easy marks because you learn them, okay? But before we get there, let's look at graphs, okay? And just to remind ourselves of what we did last time, okay, for the beginning, it says for the general equation, how does the concentration of the reactants and products change during a chemical reaction, and how does the rates of the forward and reverse reactions change during the reaction? That's really important. So what I'm going to do is I'm going to give you 2 minutes, and I want you to see if, even if it's in shorthand, if you can answer those 2 questions for me, okay? So I'm giving you 2 minutes, and those 2 minutes start now. How did we do, grade 12s? Okay, so let's look at that quickly. So here we go. Now, how does the concentration of the reactants in the products change? Well, this is what you need to remember, and this is, of course, important stuff to remember when we do KC. The point here is that, remember, for A, and the square brackets mean concentration. So what if I say square bracket A, I mean the concentration of A. Initially, the concentration of A and the concentration of B will decrease because we're using it up. Okay, so initially it decreases, and then C and D will initially start to increase. Okay, that makes a lot of sense, but after some time, chemical equilibrium is reached. When it is reached, this is really important, the concentration of the reactants and the products remain constant. Please, grade 12s, you cannot tell me that the concentration is equal, because it's not. Remember, if it was equal, then your Kc value would be 1, and that we know is not the case. In fact, we very rarely get a Kc value of 1. Doesn't mean it's not possible, but it's very rare. So the Kc value can't necessarily be 1, so we can't say the concentrations are equal, but we do say the concentrations remain constant. And that's really important, because it means that when we look at the reaction, it's going to look as if it stopped. Now, with the rate, what happens here is the rate of the forward reaction starts really, really high because we have lots of A and B. Okay, and because we have lots of reactant, the reactants are going to want to make each other, which makes the forward reaction very fast. Okay, then that also means that the reverse reaction for C and D actually is 0 to start off with. Then once we've made a little bit of C and D, the C and D can start reacting. And the C and D reaction starts off slowly, but it will eventually increase because we have more. A and B starts off fast, starts to decrease because we have less as we go along. And eventually, okay, the forward reaction rate will become constant, the reverse reaction rate will become constant, and what's really important here is they will become equal to each other. That's the important part. So at equilibrium, the concentrations remain constant and the rate is equal. So as fast as I'm making product is making reactant. Why is this important to know? Why am I making a big deal out of this now? Because we need to look at graphs. Now, I've specifically chosen the N2O4 to NO2 graph because this is an application. So when we make nitrogen dioxide gas, we always get N2O4 with the dinitrogen tetraoxide. Hate these names. Okay, we always get an equilibrium. Now, the important thing here is that the N2O4 is a very light brown gas, the NO2 is a very dark brown gas. And if we look at this graph, so I have a graph here. Now, this is a rate graph, which helps us for equilibrium. So you know what rate graphs are, and this graph is plotted what happens with the N2O4 and the NO2 over time. And you can see with the blue graph over here, okay, which starts here at 1, so it starts over there, that we start with a lot of N2O4, and over time it slowly decreases, and eventually, and this is important, over here, it goes parallel to the axis. That means that the concentration remains constant. At the same time that we are making NO2, the NO2 starts at nothing, it gets faster and faster, it gets steeper, and then we end up with it at a flat rate. Okay, now because it goes parallel, all right, that means for us that now it's reached equilibrium. It has not finished. It's an equilibrium reaction. It's reached equilibrium. And the gradient here and the gradient there must be equal, but they'll be in the opposite, they'll have opposite signs because one's getting faster, one's getting slower. Okay? Now, if we have a sample of the dinitrogen tetraoxide, that's this, trapped in a sealed gas syringe and left to stand in the sun, the sun means an increase in temperature. Okay, and this causes the sample of gas to become darker brown. First question, what can you deduce from this observation? And secondly, how could this change be reversed without changing temperature? Now, a question like this, and I want to talk through it, I'm going to give you the answer now as well. Here, I'm changing equilibrium. Now, by increasing the temperature, what we have done is we have favored making product, okay? We have favored making products that goes dark brown, and it's a very dark brown, okay, if you leave it there. So what we've done here is we've gone, well, we've increased temperature, and it's favored the forward reaction, okay? So this is me thinking it out. I'm going to write it out nicely in a second. Now I don't go, well, forward, nah, I'm glad you understood anything I just said. Temperature, remember we go, well, if we increase temperature, it must favor the endothermic reaction, okay? So now, I know an increase in temperature also favors the endothermic reaction, and in this case, I know it's going to go to the forward reaction. That tells me that the forward reaction is endothermic. So that's the first thing here, is what can we deduce from this? Okay, so what do we get? Well, I know that the forward reaction is an endothermic reaction because the forward reaction was favored. Okay, delta H was greater than 0. They love questions like this, by the way, grade 12s. All right, so here, this is why, and I said this to you last week, you cannot learn that an increase in temperature always favors the forward or always favors the reverse. Because I could have quite easily reversed this reaction around and actually given it to you like this and said we've got NO2 becoming N2O4. Okay? And then it would become darker brown in the sun, and that would favor the reverse reaction, which would then mean that the reverse reaction is endothermic. Okay, so now you need to be careful with these, okay? Increasing temperature favors the endothermic reaction. In this case, that happened to be the forward reaction. Now, I love this next question. So now it says, how could this change be reversed without changing the temperature? So, now we go back here and we say, well, we've got gas particles, and we think about it and we go, well, what are the things that change equilibrium? Concentration, but now it's trapped in a sealed gas syringe, so can't change anything about concentration. Brilliant. catalyst, sealed gas syringe, can't add a catalyst. We've done temperature. It's a gas, so surface area, which is only for rate, makes no difference. That leaves me with one option, pressure, okay? But we want to reverse the trend. So now it's gone dark brown. I now know I've got to change the pressure, and now we've got to favor making the light brown. So now we look, with pressure, we look at number of molecules. There's 2 on the right, only 1 on the left. So with pressure, if I increase pressure, your equilibrium shifts to the side with the least number of molecules. We don't care about the size. If I decrease pressure, it shifts to the base with the most number of molecules. And the reason why it does that is because the particles need to collide with the sides of the container. Pressure is the number of collisions. If I increase pressure, it wants to make sure that there's less collisions, and if there's less particles, then there's less collisions. If I decrease pressure, it wants to increase the number of collisions, so it goes to the side with the most number of particles. So in this case, because I want to reverse it, I want to make it lighter brown. The lighter brown side is the one with the least number of particles. I will increase the pressure. Now, I've written this in a lot of detail where it says increasing pressure favors the side with the least number of gas moles, therefore the reverse reaction is favored. What's in brackets you don't necessarily need to write. I've put it to make sure that you understand where I'm going to. And it's the number of moles of gas or the number of particles. It has nothing to do with the size. Okay? Sure. Okay, so grade 12s, we're going to take a small little break. And then when we get back, we are going to hit a question with a graph and see how we do. Okay, so I'll see you in a little bit. Okay, welcome back, grade 12s, and now we get into the nitty-gritty. Okay, so here's the equation, and then I'm going to show you the graph. Okay, and it says the following equation represents a reversible reaction that has reached equilibrium at 470 degrees Celsius. That is important because remember, your Kc value is temperature dependent. So it's very likely we're going to have a Kc something along the way. Now, this is nitrogen and hydrogen goes to ammonia. In fact, this is the Harbour process. Okay, that's why I chose it. Now, a change was then made to the ammonia in the equilibrium mixture at T2. I'm going to show you the graph in a second. And a graph showing the effect of this change is drawn below. So the graph is not drawn to scale, and here is the graph, okay? And this was done at 470 degrees Celsius. Now, when we look at this, we go, I know that we had equilibrium at between T1 and T2 because all the lines are straight. The concentration remains constant. Then something happened, okay? That something shifts the equilibrium, okay, until we get to T3. At T3, this new equilibrium is established, and I know it is because the lines go straight again. We are going to want to know what happens. Now, what they said to you is we made a change to the NO3, which we can see with that part over here. Okay, that's the change to NO3. Looking at it, we've got to say to ourselves, well, we know what they did is that if you look at it, the amount of gas has increased. So we know what change they made. With a graph like this, you then need to look at what happens to the rate. Now, N2 and H2 are part of the forward reaction, and NH3 is part of the reverse reaction. Okay? So those rates change when I change the NH3. Okay, so I've now given you, let's just put this, I've given you some hints as to what's going on here. Okay, now I'm going to show you the questions. And I'm going to give you 2 minutes because I've given you some of the answers already. I'm going to give you 2 minutes to see how far you get with answering these, okay? So I'm going to show you the questions, and I'll flip between the graph and the questions, okay? But I'm going to give you 2 minutes, and your 2 minutes, let me give you the first set of questions, starts now. So, how did we do? Okay, I'm hoping the first two questions weren't an issue because we actually did those together. Because now, with the first two questions, remember I said to you that, well, I told you what the meaning of the horizontal lines were. It means that the system is in equilibrium. Okay, I did that with you. Then it said state the change that was made, and remember we look at the graph, and the point here is that this concentration increased. You can see it. So that means, or the amount of moles increased. So that means that the concentration of the ammonia was increased. You could even have written, we added ammonia into the system. However you want to write it, it doesn't actually matter. Okay, as long as you're telling me that we have more NH3 than when we started. So that's important. Now, this is the fun question. Now it says, explain how the change mentioned in question 1.2 affected the concentration of the H2 and the N2 gases as shown. Now watch what happens. So my gas comes along, okay, and what I want you to see here, okay, is that the hydrogen increases and then goes flat. The N2 increases and then goes flat. Also take note of this. The ammonia decreases again before it goes flat. It doesn't go back to its original position, but by adding ammonia, here we go, adding ammonia into the system, it's a product. The system needs to use up that product and therefore makes more reactant. So we increase the amount of N2 and H2 in the system. And that's the important part here. Okay, so how would we write this down? So here we go. So when the concentration of the ammonia is increased, the reverse reaction is favored. So there's important words here. Reverse reaction is favored. This decreases the amount of excess NH3 that we put in, which then increases the N2 and H2 until a new equilibrium is established. Okay, so what am I looking for when you write these answers? First, tell me what happened, how did the reaction react to that, and what was the result? And it's the way to remember it is what's the stress, how does the equilibrium shift, what's the result on the concentration? Okay, very, 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 very important. So let's go on to the applications that are really important here on this. The first one is the Harbour process. In the Harbour process, we need to take note of the fact that it is an exothermic forward reaction. It's all gases. Harbour process is one of the steps in making ammonium-based fertilizers, which is why it's important. And also the thing about the Harbour process is we're one of the few countries that actually have a license to use it. We've got the license from Germany. Yay, very important. So with temperature, and this whole section in the applications is we have to make a compromise between rate, yield, and cost, because it's all got to do with the cost and making money. It's in industry. If I increase the temperature of this reaction, what will happen is it's going to favor the reverse reaction. That is a problem. Okay, so we go fine, we won't increase the temperature, we want to favor the, oh, no, that's not what I wanted. Oh, no, let's go back, there we go. It doesn't like me today, but it's all right. So let's not increase the temperature, that's silly. It's an exothermic forward reaction. To favor the forward reaction, we decrease temperature. That favors the forward reaction. However, if I decrease it too much, it decreases the rate. Goes too slowly, doesn't matter how much ammonia we make, it takes too long, so we make a compromise, okay? And in fact, the temperature condition for this is about 450 to 550 actually, degrees Celsius. Why am I doing this? Because you have to know these conditions, okay? 550 degrees Celsius, so that's the temperature. Then when we look at the next thing that we can change, that's pressure. Now pressure, there are 4 particles on this side, there are 2 on this side. So what this means for us is if we increase the pressure, we will favor the forward reaction. Yay, very, very nice, but high pressures are very, very expensive, so they're still going to make another compromise in terms of the cost. Increasing the pressure will absolutely increase the rate because it increases concentration. So and it doesn't sound like much of a compromise, but it is, they do this at around 200 atmospheres. So what that means, Gr12s, is that the pressure inside the reaction vessel is 200 times the pressure you feel when you're down in Durban at the coast. That's 1 atmosphere's worth of pressure. It's 200 times 100 kilopascals or thereabouts. It's lots. You would be squashed in that reaction vessel, okay? Not good for us as humans. The next thing we can look at is a catalyst. Absolutely can use a catalyst. And why do we use a catalyst? Because a catalyst increases the rate. It has nothing to do with the equilibrium. It just means it gets there faster. And we use iron or iron oxide. Okay? Guys, please learn this. It's the one catalyst we don't actually really ever write into our equation, but you do need to know it, iron or iron oxide. Okay? The other thing we can do, which is what they do in industry, is they continually add. So we add all the time N2 and H2, okay, because by adding in the reactants, we favor making products, and we remove the NH3. So we take NH3 away, that continually makes products, okay? The next one is the contact process, and this is only the second step in the contact process. This equation is not the contact process as a whole. It's the second step in the contact process. It's actually the step that gives it its name, which I'll deal with in a second. Here, delta H is less than 0, so this is exothermic. So same as with the Harbour process, if I decrease the temperature, I favor the forward reaction, but that in itself decreases the rate, and that's a problem because if the rate gets too low, then it happens too slowly, and then we don't make money, so we make a compromise, and this happens at about 450 degrees Celsius. Happy? Good. Then, now we look at pressure again, and we go, well, this is 3, this is 2, so logically speaking, if I increase the pressure, we would favor the forward reaction, which is what we want. But this is where yield comes into play. We actually get a really high yield, so we get a lot of SO3 at atmospheric pressure. So now industry goes, well, if we're getting a high yield anyway, why increase the cost and the danger, because it's dangerous to work at high pressures, by increasing the pressure? Because actually it's not going to make the yield that much more. So it's not worth the cost for the amount of yield we get, for how much SO3 we get at the end. So this happens at 1 atmosphere, which makes it easier for us. Okay, great. Then this catalyst, very, very important, increases rate, and we use vanadium pentoxide. Vanadium. I'm forgetting how to spell today. Okay, let's try that again, shall we? Ooh, look at that. Really doesn't like me. Vanadium. There we go, vanadium pentoxide. Pent is for 5. Okay, and often we will actually write it in over there. Catalyst increases the rate, yay, we get it faster. This is the reason why it's called the contact process, because this is a contact catalyst. We actually pass the SO2 and O2 over the vanadium pentoxide. Okay, it comes in contact. So all catalysts have to come to contact. Anyway, it doesn't matter. The vanadium pentoxide is quite interesting because we mine vanadium. South Africa has vanadium mines. It's very dangerous to mine vanadium, and the miners, if they don't take sufficient precautions, get something very close to the same sort of thing as asbestosis, it damages their lungs, and it makes them very, very sick, and it's a very painful way to die. So that's not nice, and I'm glad I don't have to do that job. Okay, but because we mine vanadium, obviously this catalyst becomes a little bit cheaper for us. The contact process is the second step in making sulfuric acid, and we are one of the largest exporters of sulfuric acid in the world. So we ship out tons and tons and tons of sulfuric acid, which is good for us because it brings in foreign currency. Okay, now you've had your business lesson for the day. Once again, same as with the Harbour process, if I increase or keep adding SO2 and O2, then I can get more SO3. If I take SO3 away, then I will also make SO3. Okay, so it's a way to increase the forward reaction. So we favor the forward reaction. By favoring the forward reaction, we get more product. Yay, we make more money. Yay, very important. Okay, so on that note, okay, we're going to take a short break, and when we come back, we are going to tackle another question. So I'll see you in a couple of minutes. Okay, are you ready, grade 12? So welcome back. We're now going to tackle a question because it's really important. And what I'm going to do is, as I read the question for you, I'm going to highlight the important information, which is what you really need to do, because often you get a little freaked out by the size of the question, just by how much information is given, but actually not that much is important. So we need to find it first. So here we go. Fertilizer Company produces ammonia on a large scale at a temperature of 450 degrees, and it doesn't want to be my friend. Let's try again. There we go. Ha! Now we can see it because it's blue. The balanced equation below represents the reaction that takes place in a sealed container. They gave us the sealed container because that means it's a closed system. We like that. Delta H is less than 0, even better. That means the forward reaction is exothermic. Then it says, to meet an increased demand for fertilizer, the management of the company instructs the engineer to make the necessary adjustments to increase the yield of ammonia. In a trial run on a small scale in the laboratory, the engineer makes adjustments to temperature, pressure, and concentration. Now, he does that and takes results, which I'm going to show you on the next slide. There we know that so he's not adding a catalyst, he's not doing anything, temperature, pressure, and concentration. So here is the graph that we get. Now, what's important with this graph is there's 3 places where he changes things. Those 3 places are here: T1, T2, T3. There were 3 things he changed: temperature, concentration, and pressure. What you have to look at is, when we look at this graph, is now you have to go, when the change was made, what happened to the rate of the reaction, and how, so in other words, what's the gradient of the graph, and what happens to the amount of each substance we have. It looks a lot more complicated than it really is, all right? So what we're going to do is, I'm going to give you the first question. So now the first question says to us, identify the changes made to the equilibrium mixture at each of the following times, T1, T2, T3. I'm going to give you a minute, okay? Yes, I'm going to give you a minute to look back. Here's the graph, and what you're going to try to do in that minute is identify what I changed to T1, T2, T3. Concentration, temperature, pressure, and how. Okay, increase, decrease, remain the same, whatever the case may be. All right? Your minute starts now. Okay, grade 12s, did some of you just go, okay, I'm done, I'm just going to wait for the minute and hope for the best? I hope not. I hope you tried. What you need to look at is the shape of the graph. So I said to you that we could have changed temperature, concentration, and pressure, okay? Now, when we look at T1 and we look at the graph and we go, well, if we look at this, we can say to ourselves, well, the only thing that's important when we look at it is there's this spike over here, and only N2 spiked. The rest didn't. And in fact, when I increased the concentration of the N2, look what happens to the H2. It got smaller, but the N3 got bigger. So the NH3 got bigger, which actually means what I did at T1 is I increased, okay, so at T1, what we did over here is I increased the concentration of the N2. I added more N2 into it, okay? Then we get to the next one and we say, fine, now what happened at T2? Watch, look at the graph. T2 does this. T2 does this increases, that increases. All at once. All three increase at once. But there's a spike. That spike tells me that something happened to the concentration. Now, there's only one way that I can increase the concentration of all the gases in my system at the same time. By increasing the pressure. If I make them into a smaller volume, so I make the volume of the container smaller, their concentrations increase because now we have the same number of particles in a smaller value, in a smaller volume, which means if I calculate their concentration, it will have gone up. So at T1, T2, we increased the pressure, okay? Now we get to T3. At T3, when we look at it, and we go, fine, the gentle change, okay? But what happens here is the rate, and if we look at it, we actually ended up with less. So we go back here and we say, fine, this is less than when we made the change. The H2, because remember this is N2, this is the NH3, this is the H2, okay, going backwards. The N2 and H2 increased how much they had than what we had before we made the change, and the NH3 got less than what I had before I made the change. So what happens is whatever I did favored the reverse reaction, and it's a gentle change, so everything had to change together. Only thing that's going to do that is temperature. So now we go, well, what did we do to the temperature to favor the reverse reaction? Well, delta H is greater than naught. I lied to you. Delta H is less than naught, which means the forward reaction is exothermic. So to favor the reverse reaction, I have to increase the temperature. Now, this question just asked what change was made. You didn't have to explain it. But the reason why these questions are so important is because you have a lot of thought process behind them, okay, to get to those answers. All right, so next part of the question. Now, so there's our graph again. Now, at which of the above times did the change made to the reaction mixture lead to a higher yield? Okay, so now we go and we look at this and we go, well, when did I get a change that meant that I ended up with more NH3 than I started with? That's really easy to see, because if you look and you go, that's bigger than the time before, that's bigger than the time before. So my answer here is going to be, when I look at it, T1 and T2. T3 isn't the answer, even though at T3 I have more NH3 than I started with. That wasn't the question. You've got to compare it to only one change before, not the beginning. Okay? Increasing the temperature did not give me a higher yield. It gave me a lower yield. That's bad. Okay, so now we can't get away from a question without an equation. So let's look here. Okay, now it says to us, the engineer now injects 5 moles of N2 and 5 moles of H2 into a 5 decimeter cubed sealed container. So there's some important information here. Let's make sure we've got it. 5 moles, 5 moles, 5 decimeters cubed at 450. Upon analysis at equilibrium, he finds that the mass of the NH3 is 20,4. Calculate the equilibrium constant. Okay? Oh, yeah, I can hear the groans. So I'm going to give you, and it's going to be 2 minutes. Okay, here's the equation. I'm going to give you 3 minutes to calculate the equilibrium constant. So you have, and the reason why I'm giving you so little time, so I can make sure I get time to do it with you. So you have 2 minutes, and those 2 minutes start now. Okay, some of you I know are like, I need more time. I know you do. You'll have more than enough time in an exam, but I want to make sure we got this. It's an equilibrium question. That means we have to use a rice or an ice table. I use rice tables, okay? But what's important here is, what I like about this question is this last little piece here, where it says that upon analysis, the equilibrium mixture, he finds that the mass is 20,4 grams of ammonia. You need to work out the number of moles of ammonia, okay? So we need the number of moles of ammonia in my container. So remember, number of moles is mass over molar mass. So this is the first thing we have to do. And the mass is 20,4, and the molar mass of ammonia is going to be 14 plus 3 times 1, that's the hydrogen. And what we get here is 1,2 moles. Now this question was actually worth a lot of marks, but that gets you marks, just being able to convert that to number of moles. So now when we have our table, remember this is how we set it up, and I like to put in a second line over here because that helps me distinguish between my reactants and products. Initially, they said to us I have 5 moles of nitrogen, 5 moles of hydrogen, no ammonia. At the end, this is why we had to work out the number of moles. We have 1,2 moles of ammonia. Now we work backwards and we go, well, if I had no moles of ammonia, I made 1,2, then I have 1,2. Also, the mole ratio line and the change line must be in the same ratio. So the 1 to 2 is easy because I have twice as much ammonia as nitrogen, so I'm going to divide by 2 to get this. To get the hydrogen, I'm going to take the 1,2 of the ammonia times by the number of moles of hydrogen I want, divide by the number of moles of ammonia I have, so I divide times by 1.5 essentially, and that gives me 1,8. Now from the nitrogen, I'm minus the 0.6, so I'm left with 4.4 moles. From the 5, I'm minus the 1.8, so I'm minusing, and plussing. Okay, minus 5 times minus 1.8 gives me 3.2. And before you think I'm completely brilliant, I do have the answers written down. But remember, concentration, oh no, that's not what I want. Concentration is number of moles of a volume. And in the question, they said to you, your volume was 5 decimeters cubed. So I'm going to have to go 4.4 divided by 5, which means here this is 0.88. This is going to have to be 3.2 divided by 5, which gives me 0.64. This is going to be 1.2 divided by 5, which gives me 0.24. Please don't forget that. From here, now I've got enough information to do the Kc, which is the concentration of my products, NH3, and it's going to be NH3 squared over the concentration of my reactants, N2, and H2 cubed. Okay, straightforward. Now we just plug everything in. I know I'm going really fast. I'm sorry, guys. So this is 0.24. That's squared. This is 0.88. This is 0.64 all cubed. And we put it into our wonderful electronic brains. I wish I could do this in my head. And what we get is a nice answer of 0.25. This wasn't a difficult rice table. The problem was this part here. Okay, the problem was remembering to calculate the 1.2, and then of course remembering that my volume was 5. Okay, which is why I highlight things on my question as we go along. Okay, so grade 12s, we're finished with equilibrium for now. We will do a little bit more when we do the exam prep. We're going to do some acids and bases next week. So keep well, keep warm because it's winter, and I will see you next week.